Hi folks, in this video we talk about doing formal proofs with the identity predicate. This is the last thing you need to know in order to know how to do all kinds of formal proofs in FOL. You've already learned how to deal with the intro and Elim rules for the quantifiers, so the identity is the last symbol that we need. It's slightly unique because this is a predicate symbol, unlike the operators like the connectives and the quantifiers, but still you'll see that we can give it the exact same formal treatment with introduction and elimination rules that we do for all of the other logical symbols. Now, identity intro is perhaps the simplest rule of all, because you know that any sentence like A equals A or B equals B is necessarily true. That can't possibly be false. The identity intro rule allows us to just assert one of those whenever we need it in a proof. Now, you might be wondering, why would we ever need that? And I'll show you with some examples a little bit later why we would. But you know this cannot be invalid because this follows from absolutely anything because it's a first order validity. Now, this rule is unique because it does not take a number. So this is like writing premise or writing assume. It's one of those very unique sorts of justifications that does not take a semicolon and a number after it. You can just assert this out of thin air in a sense, just like you can write assume out of thin air as long as you're starting a new subproof. The identity elim rule is how we use an identity symbol. So you cannot apply identity elim unless you already know an identity. Like on line 5, I know that A and B are two names for the same object, A equals B. And let's say I know something else about A, like A has property P. Well, if A has P and A is B, then I can just substitute in B for wherever A appears. So here's how you can read these identity symbols. Wherever A appears, I can put a B, or wherever B appears, I can put an A. So this is a kind of substitution rule that allows you to go in either direction. It's essential, though, that you have two separate lines to cite. So identity elim requires two lines to cite. You cannot just cite one line, and you cannot cite three lines. It takes exactly two. It takes the identity symbol that you're trading on, you're using for a substitution, and then it takes the location of the argument place into which you are substituting. That's the line 6. Okay, this is the rule. This should be completely familiar from algebra. For example, if I know that A equals 3 in algebra, and I know that some other formula in which A appears, then I can just insert the number 3. So this symbol works just like you've seen it work in mathematics before. Okay, some other points about the identity elim rule. It's a very powerful rule. So I can substitute wherever I have an A, B for all or some of the occurrences of A. So notice this example. I have a 4-place predicate R. So this is a very complex relation. And the name A appears in 2 different argument places. Well, the identity elim rule allows me to do multiple different things. I could substitute B in for both of those A's and cite identity elim 5.6, or I could just do one of those locations and cite identity elim 5.6. I could have also done the other location as well and just done that one. So you can see that as long as these substitutions are allowed because A and B are naming the same object, all of those types of substitutions would be valid inferences. So all of them are going to be licensed by our identity elim rule. Okay, so one last point, you can go in the opposite direction. So if I had B in there originally, I could always substitute A in there and the citation would be the exact same. So think of identity elim as a substitution rule where anywhere you have one of those names, you could put the other name. It allows you to go in either direction. All right, let's look at a concrete example so you can see how this might actually function. Here's an argument that depends upon the identity predicate for its validity. So pause your videos and see if you can figure out this argument on your own before we talk about it. Okay, let's talk about it now. Notice my conclusion is a wide scope negation. So these premises don't tell me what I should be doing first. Of course, it might be possible to start with one of those premises, but when you look at the wide scope negation conclusion, the first thing I want you to think is to do a reductio. So this is not the only way to do the proof, but I think this is the most straightforward way. I'll talk about some other ways at the end of this video. So if I wanted to do a reductio, the first thing I would assume is the opposite of my conclusion, the thing inside the scope of the negation symbol. That would be A equals B. Now notice what happens when I do that. Now I have a wide scope, I have an atomic sentence that's just the identity predicate. So this is going to allow me to do some sort of substitutions. There's different sorts of substitutions I could do. I could do, for the argument B here, I could put an A there like I did and cite identity elim 3.4. I could have also put a B in for this A. So there's multiple legitimately equally good ways of doing this proof. But once I do that substitution, notice what I have here. I have a conjunction of my line 2 and my line 5. So I'm starting to build something that is similar to this universal quantifier. Of course, you might have instantiated the universal quantifier next too. That would be equally good. So you could have transposed those lines if you didn't see to put those conjuncts together yet. But notice when I do universal Elim now, this thing that I get on line 7 is exactly the opposite of what I have on line 6. Those perfectly contradict each other. One of them is just the same formula with a negation wide scope around it. That allows me to introduce the contradiction symbol. Now, if you didn't know that we were trying to get a contradiction symbol, then you have to back up and think about the Boolean rules. You have to go back to your Boolean logic. Whenever I assumed the opposite of my conclusion to do a reductio, I knew that I was now going for a contradiction symbol to finish that proof. So negation intro is the last line I need to cite. But notice, this proof would not have worked if I couldn't have done a substitution with the identity predicate, because this says nothing can be both P and Q. But look, A has property P and B has property Q. So that means that they cannot possibly be the same object. Otherwise, something would have both P and Q, and that would be impossible. So there's a little argument whose validity depends essentially on the identity predicate. Now, this goes back to the order of operations that I talked about earlier, when we can instantiate this universal quantifier or not. So this is sort of a hard question, but I really want you to think about this. Pause your videos and see if you can figure out if there's something wrong with this proof. Where does it go wrong, if it goes wrong at all? So pause your videos and try to figure this out. Okay, that was your chance to pause your videos. The answer is it doesn't go wrong anywhere. That might be counterintuitive because previously you've seen examples where what you need to do is first start a subproof before you can start instantiating your universal quantifiers. Don't instantiate your universal quantifiers too early, I've told you before. Now, so you might think this is a problem. I've instantiated before I started that subproof, but this is actually totally fine. I could have done this substitution with B for line 2 and inserted a B where this A appears. That's actually completely valid. So that's different than the identity Elim I did before, but that's okay. And the place that I instantiated the universal quantifier is different than I did before, but that's also okay. So if you were worried, if you thought that this proof went wrong on line 4, you were probably thinking about something like this. Here is the difference. Because look at this proof. Oh, you can see I've got the old symbol for the universal quantifier here, but hopefully you recognize these quantifier symbols because these are equivalent to our A and our E. This is just the alternate notation, which is incredibly common in philosophy. So it's really good to be familiar with that notation anyway. But what's gone wrong here doesn't have to do with those using different symbols for these quantifiers. What's gone wrong here is look at my name N. My arbitrary name N, you see, why did I assume at N P of N on line 4? It's because I knew an existential and I was doing existential Elim. That requires an arbitrary constant. N is functioning as an arbitrary object in the domain that has property P. And the restriction on that is that N is not allowed to appear anywhere outside of this subproof. And that's why this is totally illegal. I cannot have N appear on line 3. I could not instantiate this universal quantifier first because that would then put it outside the subproof, my name N, and then that would make this argument potentially invalid. It would violate one of the rules that ensures that our inferences are always valid. So when the names are arbitrary, don't instantiate your universal quantifiers too soon. The difference is on that identity proof, these are just regular names A and B. When I do this reductio on not A equals B, I don't need an arbitrary name in order to do this. So think about those restrictions on arbitrary names. That's when you need to be careful about instantiating your universal quantifiers too soon. Otherwise, there's many different places you might be able to legitimately instantiate the universal quantifiers. Okay, so that's the basics about how identity intro and identity Elim works. Thanks.